Hello, it's Keith here, and this is lesson 2 of the basics series. This is where we look at the absolute fundamentals of assembly and processors and things like that. It's really designed as some background for if you are wanting to start programming retro computers, learning assembly, and you need a bit of a warm-up and some discussion of the general terms so that you don't jump into it and struggle with the early stuff. Now, my main series, I've got a series on pretty much every major processor, at least the ones that we'll be discussing here, and those tend to go in very fast and assume that you will either be able to grasp the concepts very quickly or you've done some background knowledge, whereas this series is here to give you that background knowledge. Now today we're going to be discussing the processor, and we're going to be going into some details of the processor and the registers that it provides. Now the registers are the tiny bits of memory within the processor that are used for calculations and also for other functions of the processor, and that's going to be very much the kind of thing we're going to be discussing today. Now we're not going to be discussing any particular process. We're going to be comparing a few and giving you some general information about how processors work. So as I say, this is going to give you the background and then move on to one of my other series. If you search for Chibi Akumas and the processor you're interested in, Z86, 502, 68000, 866 ARM, TMS 9900, PDP-11, I've done them all. So if you search for the process you're actually interested in Chibi Akumas on YouTube, you should get the videos with the details of actually programming. Today we're just discussing theory. Now let's go over to my book and let's have a look at some processors and how the registers differ, just very quickly, just to make the point of how wildly different processors work. So here is my beloved Z80, and these are the registers that it has. It has quite a lot. Now you'll see that we have this one marked A at the top, which is the accumulator. We'll discuss accumulators in a moment. We have HL, B, C, D, E. These are pairs of 8-bit registers that work as a 16-bit pair. We then got some index registers and a few others, and we'll discuss those as well. The point I'm making here is we've got a variety of them, and some of them are even 16-bit. That's the Z80. Now if we go over to the 6502, well, we don't have many registers at all here, and there's no 16-bit ones, which might seem a little bit strange, and that's because the 6502 works very differently to the Z80. So the fact that it's got fewer registers isn't a problem for it, because it just works completely differently, and again, we'll discuss all of that in later lessons. Now, alternatively, if we go to the 68,000 here, now here's the 68,000 registers, and we have, you see, these ranges D0 to D7, A0 to A6. These are much more generic, and that's because basically when you're in the 8-bit world, registers have very specific and limited purposes, whereas when you go to 16-bit and onwards, you generally have a lot of registers that can do pretty much anything. They become much more flexible. So that's the sort of difference, and the PDP-11 and the ARM are much more like the 68,000 and the 8-bit processors. So I'd say the point I'm just making there is, we've got a variety of different registers. Now that's an excerpt from my book. We're not going to go into it anymore. If you're interested, you can get my book from Amazon. I've got the advert showing up here, but you don't need the book to follow this series. This series is self-contained. It's based on the first chapter of the book anyway. So I just say you're welcome to buy it, but you don't need it to follow this series at all. Now, we saw those, and we saw a variety of registers. The most important of those on the 8-bit systems is the accumulator register, which is often referred to as A. Now, in the 16 and 32-bit world, as I say, most times the registers can do any job. But on the 8-bit processors, things are a lot more limited, and usually what you have is one, or in occasions on the 6800 based processors, you have two. But on most of these 8-bit processors, you have a single accumulator, which is your core mathematics register. Basically, as I mentioned before, if you're doing calculations, I think thinking of things as a calculator often works quite well. And in this case, you could think of your accumulator as being the result of the current calculation, because the accumulator can only store one single value, and you will need to then use that result and add other things to it, or subtract them, of course, do your continued calculations on the value in the accumulator, but then you'll need to move that accumulator value either into another register or into memory once you need to work on another calculation, and then you might need to bring that accumulator back later on. For example, maybe you're calculating the X position of your player, then you're calculating the Y position of your player. Well, you need to calculate that X position in the accumulator, move it into memory, then work on the Y position, move that into memory, and then bring them both back, and so you can position your sprite on the screen in the place it's supposed to be. It sounds like a ridiculous load of effort, but that is the way we have to work in 8-bit processors, because as I say, really, typically the accumulator is the only one that can do these mathematical jobs we're going to need. As I say though, don't worry about that too much, because you'll see that when you actually start to look at the processor that you're working on. Just for this point, if you're thinking of 8-bit processors, expect your accumulator to be doing all of the heavy lifting of calculations. Now, we do have a variety of other special registers which have special purposes. Now, the most important of these in some ways is the program counter. Now, when you are writing your code, you will be creating lines of code that will then be compiled into bytes, which your processor will actually come to execute. Now, the processor itself really doesn't have any magic within it. It's got its own registers for working out what it's actually got to do next. And the program counter is effectively a bit like if you've got a list of things you need to do, a to-do list, and you're going through the list and you're going through them in order. That's exactly what your processor is doing with your assembled program. So in the same way as you might have your finger pointing to the next job you need to do so you don't forget which ones you've done and which ones you're doing next, the processor is using the program counter register to point to the memory address that is the next thing that it needs to do. And so the program counter is an internal function of the processor that allows it to remember the memory address it's looking at next. Now, the program counter in some 16-bit and later processors does have functions that you can use it for. You can use it as actually part of calculations for things, but it's also used for things like when you're calling subroutines and returning, the program counter is used. So at the very least, you need to know that the program counter exists and know that it has this important function of remembering the memory address of the next line of code that's going to be run. But don't be surprised when you see it. Although it's not something as a beginner you necessarily need to worry about actually doing anything to it, because it's really an internal thing that is built into the processor itself. Another thing that's built into the processor itself, which you need to have an understanding of the purpose of, is the flags register, also known as condition codes. The names of some of these differ slightly depending on the processor, but the purpose is basically the same. Now, the flags register relates to acting upon previous results of calculations. Now, on all of our processors, it does vary a little bit depending on the processor, but on all of our processors, we're going to be doing various calculations. You know, maybe we are subtracting, maybe we are comparing two values and things like that. And we are going to need to do things depending on the result of those comparisons. You know, our player's just lost a life. Have they got 3 lives? Well, we subtract, it goes down to 2, then it goes down to 1. But when it gets down to 0, we're going to want to jump to the game over sequence, and that is the kind of things that our flags do. Now, our flags are typically just single bits within a register, known as the flags register, the condition code register, depending on the processor. But the flags are basically a set of bits that will be set or cleared based on previous calculations, and then we can test those flags and change the events in our codes accordingly. Often with like the Z80, we can branch to a subroutine based on a flag. On a lot of other systems, we actually jump over parts of code based on flags. So if the 0 flag set, we jump to our game over screen. If the result of comparing the high score and the current score, if the high score is greater, we jump to this update high score routine, things like that. Now, each of these flags is a single bit, and they will have different definitions. I've got 3 examples here. It will depend on your processor, but the 0 flag will be set if the previous calculation resulted in the value 0. The overflow flag will be set or cleared if a value has accidentally flipped its sign. Now, that's a bit complex, so don't worry about that. You'll probably not need it as a beginner. Now, the carry flag is a little bit interesting, and we'll just discuss them quickly here. Now, if you're familiar with doing old-fashioned mathematics on bits of paper, you might have done addition and things where you've got 2 values that you need to add together, and you're going to build up your total on this result line, but then you've got a carry line below that. So, for example, if we're adding 9 and 1, well, our value, that is going to add up to 10. So we put a digit of 0 here, and we put 1 in our carry here. And then we're effectively adding 0 and 1 here, but we're also adding our carry line here. And so that will become 2. So 9 plus 11 equals 20. And our carry was used to carry the value over from a digit. Now, here we're working in digits, but on our processors we'll be working in bytes. But when a byte overflows, a carry flag will be set. Now, that's one example with regards to doing addition. Another interesting example is Now that's how a carry would be used for addition, but the other example is for rotation. Now suppose we've got this value here, and this is 8 bits, which is a single byte. We're going to cover a lot of this later on, so don't worry if you don't quite understand that. But if we've got a value like this and we decide to rotate it to the left by 1 bit, well, we might see something like this happen. We'll shift by 1 bit here, and a new 0 bit will be inserted here, possibly, depending on the command we're using. But 1 bit has been pushed out of the byte, and that will be pushed into the carry on most processors. So that's another function of the carry. It's when you're doing rotation and bits are pushed out of the byte or the word, depending on the command you're using. Now, as I say, I know this is going to be a little bit confusing, and you don't need to worry about it if you don't understand it at this point, because all of this will come back later on when you're actually looking at the processor you're interested in and the commands. But at the moment, I'm just making the point that the carry has multiple functions, and it's to do with data that has been pushed out of other registers as a result of calculations. So I just wanted to give you some background there. That's why we're covering that. So don't worry about it if it's too complex for you at this stage. Now, the carry becomes quite important on 8-bit processors, because even though our processor is only 8-bit, we're going to need to work in 16 bits because, surprise, surprise, an 8-bit value can only go from 0 to 255, and having a processor that can only access 256 bytes of memory wouldn't be very good. So an 8-bit processor usually has at least a 16-bit address bus, and that means we're going to have to deal with 16-bit values to calculate addresses, and that means we're going to have some way of calculating the overflow from an 8-bit value. Now, the Z80 has 16-bit pairs where you can combine two 8-bit registers to make a 16-bit value, but the 6502 does not. And again, this is where the carry comes in. And again, we're just going to cover this very quickly and simply, but what we will do is often we would clear the carry, add two values together for our low byte, and then add our two values together for our high byte with the carry. And this allows the carry from the low byte to overflow into the high byte in the same way as you saw when I did the addition of 2 digits on the blackboard before. You can do addition of 2 bytes and use the carry to carry the overflow into the second byte there. Again, you will see all of that later on when you're actually looking at the processes you're interested in. I've got examples of the carry on those processes, but again, I just want to make the point that when you're looking at these processes and you're going to hear these terms like carry, I think it's good to give you some background and some examples so that you know what it actually means in practical terms, so that when you see it you'll be a bit more familiar. Okay, next thing we're going to discuss is the concept of ports, and this is another one that differs quite surprisingly. The Z80 and the 8086 are basically different from pretty much everyone else, which is rather a surprise. Now, the 8086 and the Z80 have special commands to access ports, and ports are relating to other pieces of hardware. Now, if you caught last week's exciting edition, you will remember I went over this board here. This is a Neo Geo CD board, and this is the main processor, but we've got all of these other processors around the place which are going to do things for us. We've got the sound chip over here, we've got some graphics chips up here, we've got, I think this is the I/O chip here. But the point I'm making is it's all split out into lots of different chips, and we need to talk to those other chips and ask them to do things for us. We might need to ask the joystick if any keys are pressed, we might need to ask the sound chip to make some sound, we might need to ask the graphics chip to show a sprite. And the way we do this is with ports. Now, on the Z80 and the 8086, we've got special commands that we can access numbered ports with, but on most other systems, these are memory mapped, and what this means is that a certain address will have a certain function. Maybe the address 9000 links to the sound chip, and the memory address 9001 links to the video chip, and we need to send data according to those pieces of hardware. Now, all of this will relate to the platform you're covering. So if you're doing the MSX on the Z80, that's going to be different to if you're doing the Sega Master System on the Z80. They're different, and of course this is true for all of them. And I've got platform specific lessons that cover how to make sounds, how to read joysticks, how to draw graphics. So it's all going to be very specific to the system you're interested in. Really, all I want you to understand at the moment is if you're on the Z80 or 8086, you've got numbered ports that have special commands to access them. If you're on another system, then it's very likely any other processor, there will be certain memory addresses that you will just read data from or write data to, and those memory addresses won't be RAM, they will actually be memory mapped hardware ports. And that's how you will access your hardware. It's all very specific to the system itself though, so don't go looking around for generic guides to making sounds on a 6502 system. You need to look at making sounds on the Commodore 64 or making sounds on the NES, because it's all very, very specific to the system that actually interests you. Now, we're now going to discuss very quickly another very important register, and that is the stack pointer. Now, in our programming, we are going to need to do work that involves more data than we can just store in our accumulator, or even in most cases in our registers. Now, if we need that data permanently, if it's the X and Y position of our player, we probably want to keep that all the time. But it might just be an intermediary calculation for what we're working on at the moment. Maybe first we're calculating the sprite that we want to show, the sprite number, and then we need to do some calculations on the X and Y position of our sprite, and then we need to get that sprite number back later on to finally show it to the screen. So we might need to store a value temporarily that we might need back later on, and that is what the stack is for. Basically, what I would suggest you think of is, if you imagine that the stack is a bit like an in tray. If you've got a lot of work to do, you might have multiple jobs. You start the day, you've got one job and you're trying to get it done, but then someone annoying comes on and says, hey, get on with this, and they give you a second job to do, so you can't continue work on the first job. So maybe you put it in your in tray, at the bottom of your in tray, and you start working on job B. But then guess what? Some rotter comes on with job C, another job that's even more important than the other two jobs, and so you put job B into your in tray on the top of job A, and now you're working on job C. You then finish job C and you take the first job out the top of your in tray, which is the last one you put in, which will be job B. You then continue working on job B, and finally you get to job A. Now this is known as last in first out, and this is the way that your stack works on most processors. Basically, you put data into your stack and it piles up, and you always take the last one out that you put in. So the first one you put in will be the last one you take out. That's the way that the stacks work, and this is, as I say, it's relating to the way that we often want to store temporary data on our processor. So if we get our blackboard up here, now if you imagine our stack here, now the stacks actually go down in memory. So if I just draw an area here, which we will pretend is our fictional stack here. Now, if we've got the value 31 and we want to store that temporarily, then we would push that onto the stack. The term is usually push, and we will put 31 there. And then let's say we've got 15 and we want to push that onto the stack, then the stack that would go here. Now, each time here, we've got a stack pointer, and the stack pointer will always point to the next position in the stack. So if we then push, let's say 5, the stack pointer will move up, and we would put 5 on the stack here. And each time the stack pointer is going up and new values are being put onto the stack. Now, as we pop them off again, well, the stack pointer goes back down and the values are removed from the stack, and we would get them back for further calculations. The stack, as I say, it's basically a temporary store, and it works in this last in first out method, and I would always think of it like a pile of papers that there may be stuff at the bottom there, but you can't get them out independently without going through the ones at the top first. That's the easiest way to get started thinking of it, because, as I say, the concept of the stack might not be something you're familiar with if you're just familiar with basic programming or basic C. They do exist in a lot of other systems, but you don't need to worry about them so much. But they are fundamental to the assembly programming, and especially with 8-bit processors where you've only got one accumulator. Well, how are you going to remember all of these intermediary values? Often the answer is the stack. Now, our processor typically will be running the lines of our program for us, and it will run them, of course, in consecutive order as the program counter will remember. But there will be times when things happen that need to be processed other than our program. Now, these are known as interrupts, and this will often come from hardware. Now, the most common of these is VBlank. Now, if you think of a screen like this screen here, if this was a CRT and even a TFT, there will be some kind of refresh procedure. And this is where the line is being drawn going down the screen, and then it gets to the bottom, and then it will jump back to the top at some point, and there will usually be a short gap in between. So the draw line will go down the screen, get to the bottom, and then there is something known as VBlank, and this is where the screen hardware tells the processor, hey, I've finished drawing the screen. And this is quite important on some systems, because systems like the NES, you can't update the video memory while the screen is drawing because it's locked. So you have to do things during VBlank. And this is a very, very short period of time because the screen is refreshing 50 or 60 times a second. It's only going to be a tiny fraction of a second that VBlank is occurring. And so you can't have a comparison or a check in your code because it's probably too fast. And so what happens is something known as an interrupt, which is literally what it sounds like. It's someone shouting at you, hey, stop what you're working on there. You've got to work on this VBlank right now because it's about to finish. This is what the interrupt is. But there are actually two kinds of interrupts, and they have rather odd names. We have what's known as maskable interrupts and non-maskable interrupts, and these are very different. So just quickly, we're going to discuss what they are. Now, as I say, interrupts will happen during our code, and they will get in the way of our code will stop, and some kind of subroutine will run. Now, generally speaking, we don't need to worry about this because the interrupt, while it's happening and stopping our code, it doesn't break our code in any way, generally speaking, so we don't need to worry about it too much. But there may be times where actually it is a problem. You know, maybe we're doing something really time critical, or maybe we're doing something that we're actually using the resources the interrupt needs. Now, generally speaking, we would know that on the Z80 there's something known as the shadow registers, and if we use those, that could cause problems for our interrupt handlers. It's not something that you're going to need to worry about too much as an absolute beginner, and generally speaking, you would probably be better off just disabling interrupts. But there's actually two kinds of interrupts that might occur. It's kind of like if you're at work and you've got two people who might try and ask you for things. Maybe you've got your the person who's beneath you, and they come and try and talk to you and you tell them to go away. And maybe your boss phones you and you can't do that because it's your boss, and you've got to deal with what they're asking for right away. Now, this is basically maskable and non-maskable interrupts. Now, maskable means that we can put a bit of masking tape over their mouth and shut them up and ignore them for a while, and non-maskable means they're going to have to be dealt with no matter what. And that's the two kinds of interrupts that we have. And maskable interrupts are typically the VBlank. Well, we probably want it to happen, but if we don't want it to happen, we can turn it off. Non-maskable is much more rare, but there were a few of these. Interestingly, the multi-phase 2 button on the old Amstrad CPC and the Spectrum and things, that was a non-maskable. A non-maskable interrupt on the Sega Master System is the pause button, strangely enough. But generally, there were two kinds. The maskable ones that we can turn off, and as a beginner we often want to do that because it means there's less we have to worry about in our programming. But say basically two kinds of interrupts, just something to bear in mind when you come across that later on. Okay, now the final thing we're going to discuss today is Endian. Now this comes to the storing of numbers, and it's a little bit weird. Now if we just go over to the blackboard, we'll discuss this quickly. Now let's suppose we've got a 16-bit hexadecimal number 1, 2, 3, 4. Now that is going to be 2 bytes. Now the first one is our high byte. We'll put a H there. That means it's got the highest value. And 3, 4 is our low byte, which means it's got the least significant value here. So we want to store that, and we want to store that in memory. And of all of our memory addresses can only store a single byte. So let's say we've got some memory here. And let's suppose we've got 4 memory addresses with consecutive addresses. So let's say this is memory address 0, and this is 01, and this is 02, and this is 03. Well, how are we going to store our 2 bytes in these addresses here? Well, the most logical thing will be to store the first one, 1, 2, in memory address 0, and 3, 4 in memory address 1. That makes perfect sense, and that's what's known as big endian, because we've stored the high byte, the biggest value byte, first, and the low byte second. So the big end has gone first and the small end has gone second. That might be the logical way to do that, but actually most processors do it the other way. This is known as big endian, and this is used by the 6800, the 68000, the 6809, and the TMS 9900, and pretty much no one else. What most processors have decided to do is the complete opposite. They store the little end first. They store 3, 4 in the 0 address and 1, 2 in the 0, 1 address. So they store the little end first, and that's known as little endian, and that's used by the Z80, 6502, 8086, PDP-11, and by default on the ARM. The ARM can technically work in big endian, but it basically never does. Now, of course, we've just looked at 2 bytes there, but if we were storing 4 bytes. If we had 1, 2, 3, 4, 5, 6, 7, 8, that's 4 bytes, and we were to store those in little endian in memory addresses 0 and onwards. Well, we would store 7, 8, then 5, 6, then 3, 4, and then 1, 2. And that's the way little endian works, and we've got a diagram of that there, which is basically what I just showed. Now, quite curiously, this apparently comes from the fictional story Gulliver's Travels, and there were apparently in that story there were 2 tribes who got into an argument about which end one should eat a boiled egg, and some of them thought you should eat it from the big end, and some thought you should eat it from the little end, and apparently terrible wars broke out over this argument. So this fictional story apparently is the source of the terms big endian and little endian. A bit strange, but it's a quite amusing story. There is also some weird things. Now, the ISO CD format actually uses something known as both endian, which I believe stores little endian followed by big endian, and this is just so that depending on the processor you can load whichever one you want. But as I say, generally speaking, little endian is the way forward. But the important thing is, if you're learning a new processor, just make sure you check what the endian is, because it will come into play when you are reading and writing data in memory. You will need to know it. Anyway, that's all we're going to be covering today. If you've liked what you've seen, please like and subscribe to see more. So I say, I do have a book available to buy on Amazon, but you don't need it. I cover all of the content I believe you need in my tutorials, this one and my other video tutorials. So it's just something if you want some printed material along the way to read. I hope you've enjoyed what you've seen today. Please, if you have, please like and subscribe. If you like the videos, YouTube recommends them to more people, and I have a happy day. And if you subscribe, then you will see the content that comes later on. Anyway, hope you've enjoyed watching today. Thanks for watching, and goodbye.